Well, I messed up something in the recording, but we're on session 3 of the testing stuff, and today I want to focus on algebraic laws. We'll do a little cleanup on the other stuff. But things like commutative, associative, De Morgan's law, reflexive things, all these kind of mathematical or algebraic laws that tell us concisely information about different values and how they work together. And what's very common is that, like, there are many domains where commutativity holds. Like Boolean algebra is commutative just as well as integers are, and operating mod some number is commutative just like integers, and associative, and so on. So a lot of these laws show up in multiple places, and I want to explore getting them encoded so I can check them. Now, like I said, I messed up in my recording somehow, so what I'm going to do is just kind of walk us through the pieces, and you'll get the short version of things for sure. Okay, so the first thing we looked at is this really Arrange-Act-Assert, and trying to find, I guess the example is really the way to look at. We tried to look at doing this kind of Arrange-Act-Assert and not having to pass anything through. So the previous version, you would capture the subject and the actual. This version, we just were trying to not do that. As it turns out, that was not successful. Okay, so we tried some things, but we couldn't get it to type check enough because the Arrange-Act-Assert, it understood the types. Well, we had to give it a little bit of help with ACT. But in the overall testing thing, it just couldn't derive the main type from that. So we got all these kind of quirky pieces, but as things go, I think I'll say we will not keep it like that. Okay, so in here, I did one small change EG. I'm trying it lowercase, even though that's not the standard. I don't know, it just kind of reads better to me. And I tried input, output becoming in and out, but in is a reserved word, so it looked awkward and didn't work. Okay. And let's go to the examples again. There, same thing, the EG. And you can see the beginnings of getting rid of this failed experiment. Okay. Now, we went back to assert 2, okay, and we added an extra condition to just kind of demonstrate how things worked. But we did some work to add file and line so you get better error reporting. If you track the file and line from the original position and pass that on through to things, when an XCTest runs, it points to the original line and gives you the error right there. If you don't do it, you end up pointing somewhere in the framework code, and we don't want that. The other thing I did was I added this little function EQ. I get tired of typing XCTAssertEquals, and so I'm just, if A equals B, return true, so skip it if it's fine, and run XCTAssertEqual if we know it's going to fail. That's a little awkward. We could just say fail, I think. But it does tell us the values that weren't equal, so that's why we get the benefit of it. All right, and not much else there. We used it in a couple places, or at least one place, to try it out. But yeah, I don't know if we'll keep that or not. All right, tests again are probably the starting point. Okay, so we got rid of this test AAA. We're focused on these assert 2s and some variations. Let's see, I guess we got rid of that too. So this is us cleaning up, saying, okay, we're not going to do tests. We're not going to explore the AAA Arrange-Act-Assert stuff anymore. So we're chopping out all the result builder stuff we did, and the examples, and the predicates, and the arrange and act and assert. All that stuff is gone now. Okay, quite a bit. All right. But now I want to move into working with the idea of commutative operators, a plus b equals b plus a. So I'm imagining a test that's something like this, 3 and 4 commutative, and you can see the file and line there. It's a little awkward, but op AB, op BA, we check both those versions, and if they're not equal, then that means they're not commutative. Okay, and so they have to be equatable objects. Okay, and that's really it for there. All right, and then this is kind of a big leap. This one, I've cleaned up XCT, check commutative a little bit with that early return, and started working on all pairs. And the idea is you give me a list of values. I'm going to make all the combinations of A and B both from the values, so kind of a cross product, and run whatever function you want on it. And so we have a version of check commutative that does that for all pairs. It takes the operator and the values and file line and runs all pairs, and on those pairs it runs check commutative. So if you gave it 10 values, you get 10 values or 100 values compared. It's all pairs. All right. Let me get to the top of, okay, here's some ints. Now we have a check parameterized that checks it does the all pairs on the ints and checks commutative with plus. Okay, again, I don't like the order. This is all kind of spiky code. All right, then I moved into different laws. So the reflexive law is part of when you want partitions. You want to make sure that, like, if you divide things by equal values, they should be in the same box. So you give it a value and you compare it to itself. So 3 equals 3 is reflexive. 3 less than or equal to 3 is reflexive. It's true, always, because they're equal. 3 less than 3 is not reflexive. Okay. Then we have symmetric. A op B equals B op A. Okay, so if A equals B, then B equals A. It's kind of back to our commutative idea. And then transitive, A less than B and B less than C implies A less than C. And we then use that to check equivalence. So equivalence says you got to be reflexive, symmetric, and transitive for your values. Now that almost would be better with our all pairs stuff, that we need to do it there. Okay, and then here's a test. This one says let's compare equality mod 3. So 3, 6, and 9 are they're all 0 mod 3. So the operation is going to decide they're equal, and they do form a partition. So all the numbers 0, 3, 6, 9, and so on, 1, 4, 7, and so on, 2, 5, 8, and so on. It forms a group of 3 different possible values and divides the integers 3 ways. Okay, so I think we're kind of working through what's the best way to specify these things and all that stuff. And then I think next time I think we've done enough that we can start test driving it for real. Maybe we'll fix the all pairs aspect of check equivalence relations first. I would love to make, I don't know, I tried making a all pairs that then ran any relationship, but I couldn't get it to type check right. It was so complicated. It had 10 T's, where these are these generic types, the same type occurring 10 times, and trying to decide if that really type checked, I guess, was beyond the compiler. And maybe I'm wrong and it couldn't be, but it seemed like it could. I don't know. But anyway, next time I think we'll continue. We'll work by getting these equivalence relations so that we can check them with all combinations, and start TDDing the rest of it, TDDing all of it into something we want to keep around for everything. So get the arguments in consistent order and get the lines and files in there where we need it, and so on. And I think once we've got the first few in, we'll go ahead and I've got a list of maybe 10 or 15 relationships that we might want to check for, and maybe we'll do some examples using it and see how useful we think it is. All right. Thanks for joining. I'm sorry I messed up the early one, but you get the 10-minute version instead of the 2-hour version. You'll probably be happy about that. Thank you. Take care. Bye-bye.